Hello again, I'm going to be solving the EDUQAS Electronics Component 2, Applications of Electronics from 2019 today. As always, I suggest you download the paper, it's in the link below, and have a go at it as well. Question 1, a simple flowchart to get us going. So we've got some blurb here with the specification. We need to count up to 12 tins and then we need to replace the box. So they've even given us the 3 things that we have to put in the flowchart. So we reset the counter. We first of all need to check if a can's passed before we add one to the count, and then we check to see if the count has got 12 yet. So first one is, has a can passed? The second one, so if yes, the can has passed, we want to count a can, so we add one to count. And then we want to check to see how many cans have passed. Is it 12? So and then we're asked to draw where these go back. Well, this one, has a can passed, goes back to immediately before it if it's no, so it'll keep looping around there until a can has passed when it'll count 1. And this one will also go back to the exact same place, because once you've counted, you want to check for the next can. You mustn't go back to before resetting the counter, otherwise it will never get to 12. Question 2, we have a capacitor and resistor circuit with a switch. When you push this switch, it will connect the top of the capacitor down to ground and the bottom of the capacitor down to ground, so that will discharge the capacitor really quickly. When you release the switch, then current will be able to flow from here, through here, down through onto the capacitor to charge it up. So we need to fill in the graph below to show what would happen. So when we push the switch, so it starts off after a long time, it's been fully charged up to whatever this side of the capacitor is connected to, and it's connected through this resistor to 5. So it starts off at 5 volts like so. When you push the switch, this is a very, very quick discharge because the resistance to capacitor resistance of the switch is tiny. So it will discharge really quickly. RC is really low. Discharge really quickly down to ground there, and then when you release the switch, then it will start to charge back up and it will aim towards 5, so it'll have a charging curve sort of like that, aiming to get to 5 there. Kind of messed that bit up there. There. Another delay circuit is constructed using a 555, configured as a monostable with a 2200 microfarad capacitor. Calculate resistance required to produce a 3-minute delay. Well, we're going to use the time period of a 555 is equal to 1.1 R times by C. So we can either rearrange that to get R equal something. I'm just going to put the numbers in. So 180, because 3 minutes is 180 seconds, is equal to 1.1 times by R times by 2200, and micro is times 10 to the minus 6. So R is equal to 180 divided by 1.1 times 2200 times 10 to the minus 6. So we put that in the calculator. Divided by 1.1 times by 2200, and then this number, this button here for times 10 to the, and just put minus 6, equals, and we get R is equal to 74,380, 74 kilo ohms. It's 2 significant figures. The calculated value of the resistance required is not part of the E24 series. How would you ensure that the specified time delay could be achieved? Well, we can use a variable resistor, and we would configure it like that, and we'll probably need 100k for that variable resistor there. Question 3a, we need to design a non-inverting amplifier by connecting the relevant components here. So you just need to learn these, the inverting amplifier, the non-inverting amplifier off by heart. So non-inverting amplifier means that the input is always connected to the non-inverting terminal. Amplifier means you have negative feedback, like so, and the rest, this one then, forgotten my resistor to ground, needs a resistor to ground, like so, and that's R2, and that's RF. The amplifier should have a voltage gain of 35. Calculate values of the components required to achieve this gain. Well, the gain is equal to 1 plus RF over R2, and we need this number to equal 35. So that's 1 plus 34 divided by 1, or 34 divided by 1 is 34 plus the 1. So we just pick ourselves nice easy numbers. So R2 will be 1, so let's put a 1 kilo ohm there, and RF will be 34, so that's 34 kilo ohms there. Okay, so RF equals 34k ohms, and R2 is equal to 1k ohms. Okay, we've got some information here. The power supply is 15 volts plus or minus, and it saturates at 13 volts. An input signal peaks at 0.3. Complete the graph to show the output. So we need to do 0.3 times by 35 to start with, and that's equal to 10.5 volts. So it's going to get as high as 10.5 volts. So that's 10, that's 11, so 10.5 is there. Now it's a non-inverting amplifier, so it's going to follow the same pattern as this. It's not going to be flipped upside down. So it's going to go through zeros at the same places. When it's at the minimum there, it's going to be the minimum there, there, oh sorry, and there. So we just need to join this up with a nice sine wave now. There we go. The input signal peak value is now increased to 0.5. So we've got 0.5 times by 35. Well, that is equal to a, can't do that in my head, 0.5 times by 35, 17.5. I can do it in my head. Right. Now we've got to notice that 17.5 is above the saturation voltage of 13 volts. So we're going to start at naught again. We go through the noughts here, 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 and here. And we're going to aim for 17.5, which is here. So I'm just going to draw a dotted line to start with of what it's going to look like. But it doesn't look like that because it can only get as high as 13 volts. So the maximum it reaches is there. So I'm just going to switch over to the pencil. So it goes up to there, it's flat across there, goes down to there. Then again, we're going to aim for 17.5, which is down there. And we're going to aim for 17.5, which is there. But we're not going to get there, we're only going to get as far as minus 13 on this side, which is that bit there, and plus 13 on this side, which is that bit there. So it goes down to there, to there, and to there. Okay, so it's this line here, and this bit here is called clipping, distortion. that's created because the power supply isn't big enough to output the full shape of the wave. So the last thing to do is just to rub off these bits here, here, and here, leaving you with the correct shape. Okay, in this question, it's all about a 7-second display. There's a lot of reading to do, but it's actually a relatively simple question. The first thing we need to do is to work out which segments we need to light up for each of these. So this one, that's segment F, that's segment E, that's segment G, and that's segment C. And this one, we also need F and E. We also need G, but instead of segment C, we want segment D. So you'll notice that those three are the same in each of the two symbols. So we now need to work out change that into a logic. So in both, we're going to want F high, we're going to want E high, we're going to want G high, which they've given for us. And for heads, we're going to want C high. And for tails, we're going to want D high, and all the rest are low. They've already given us A. And that will turn off this one, and this one for heads, or this one, and this one for tails. So now we need to make a circuit to make it work. And we want to make it so that E, F, and G are always high. So they've already done G for you. So we just need to they've given you a big clue because they've shown you how G would work. So E, F, and G are always high. B is always low, so we can just connect that straight to ground. Now we just need to work out what H and T are. So if the output of the AND gate is high, then H needs to be displayed for heads. So we want C to be high. So we connect C. Oh look, it's even in a perfect line for you. And then if the output of the AND gate is low, we want D to be high. So we use a NOT gate to make the output of the AND gate. If that's low, then that will be high. And then that goes and connects to there. Question 5. Once again, we've got a big block diagram and a big circuit diagram. I'll let you read that. Write down the Boolean equation for the red. Well, here's red. So we've got A and we've got B, and they're ORed together. So it's A or B. Write down the Boolean equation for the yellow. Well, yellow is D or not C. So C with a bar on. Don't forget questions like this that don't have a dotted line. Add the connections to the diagram to show that the counter resets on the 10th pulse. A is the least significant bit. Well, the 10th pulse then would be 1, 0, 1, 0. And that's D, C, B, A. So we need D and B, because that's equal to 10 in decimal. So D and B. So there's B. And we also need D. Take that from there. Now we need to fill in this truth table. So red is just A or B. So that's going to be 0, 1, 1, 1. If either of these is high, we're going to put a 1 here. Blue, we didn't do blue, so blue is just not B. So it's the opposite of this one. So it's going to be 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Don't need that one. Green is not C, so it's the opposite of this one. 1, 1, 1, 1, 0, 0, 0, 0, 1, 1. and yellow is what we did here. So it's not C, which is the same as green, or D. So it's the OR of these two columns. So 1, 1, 1, 1, 0, 0, 0, 0, 1, 1. Like that. Question 6. We've got a automatic lighting system with a simple block diagram there. And we're asked to give a reason for using the Schmidt trigger in this application. Well, so the Schmidt trigger will mean that the light, once it either flicks on or it flicks off, it will take a long swing on the input voltage for it to change to the other one. So it'll stop the light from flickering. To stop the light from flickering, when it is just turning on or off, e.g. if a bird flew over it. You don't have to give an example. At A level, it's definitely worth always giving an example when you're trying to define something. Okay, this is now, we're going to use this logic here for the Schmidt, and we're going to apply it to this input. So this is the output of a sensor, it's the input of our Schmidt, and we're going to see what happens here. Now, remember, it's a Schmidt inverter, so it's going to flip it upside down. So when this is very low, this is going to be high. When this is very high, this is going to be low. So now we need to work out when it does everything. So the first thing we should do is we should draw in these values. So at 4 volts and 2 volts. So get 4 volts here, and we just draw like a dotted line across there, and 2 volts. Okay, so those are the thresholds then. So it's going to start high because this starts on very low. Now what you have to do now is just be careful. Does it change here or does it change here? Well, it's going to, the output changes from a logical 1 to a logical 0 when a rising input reaches 4 volts. So we're going to have a change there. And when a falling input reaches 2 volts, so we're going to have a change there. So it's going to be that one and that one, which is going to create the change. So all we do is we drop those down across the page to here, and then that will create our falling line there. And then we drop this one down the page to there. This goes along here. And then we've got to just be careful that we get 6 volts and 0 volts. So yeah, that's right. 6 volts and 0 volts here. Right, and that's the shape. So the lights switch on at 0600 hours and they switch off at 2000 hours. Oh no, sorry, they switch off at 0600 hours and they switch back on at 2000 hours. So to do Schmidt questions, always draw on the graph. It makes it very, very easy. When you draw on the graph, you identify the switching points. So it will go from high to low when you get the higher of the two thresholds, and it will go from low to high when you get the lower of the two thresholds. But draw on the graph and it makes it very easy. Question 7. So we have a pulse generator which is connected to a decade counter. And the decade counter is going to have one of these high at any one time, and every time it receives a pulse, the rising edge here, that will clock and it will move on to the next one. If you take the reset line high, then it will go back to this one being high and all of the rest being low. So the first part of the question is about the pulse generator. So here's an astable circuit. To Determine the mark space ratio of this circuit. So the mark space ratio of this circuit is the ratio of these resistors. It's R1 plus R2 divided by R2. So it's going to be 47,000 plus 10,000 divided by 10,000. Well, the thousands obviously cancel, and you've got 57 to 10. Now always present your answer as a ratio. You could write it 5.7 to 1 if you wanted, but do not write 5.7. That's not written as a ratio. You could probably get away with that as well, especially if you said which one was which. So, and the mark space ratio comes about because when the capacitor is charging, it's charging through here, through that resistor and that resistor, but when it's discharging, it's only discharging through here down to pin 7, which is connected internally to ground. So it discharges through there, but charges up through there. So it charges through 2 resistors, which takes longer than discharging. So it takes longer on the mark, on the high bit, than it does on the space. So that will be 5.7, and that will be 1 of whatever units it is. Calculate the frequency of the astable. We need to use the frequency of an astable equation, which I either have to remember, or I think it's given for you up on the sheet. R1 plus, now you put 2 R2s here, times by C. And that's because when you're charging, it's R1 plus R2, and when you're discharging, it's just R2. So you add both of those together and you get R1 plus 2 R2s in there. Times by C, so we can just work all that out. So we've got 1.44 divided by R1 is this resistor here, they even tell you, plus 2 times by this resistor here, which is 10,000, times by the capacitor. Now don't go over the line there. The capacitor is 220 times 10 to the minus 6, because it's microfarads there. So let's do that. 1.44 divided by, and then we put all of this in brackets, 470. And times by 220 times 10 to the minus 6, close that bracket, and we get 72 over 73, which is 0.97 rounds. No, I've missed a 0. 0.09, and the 7 there rounds up because of the 6 there, so that'll be an 8 hertz. So quite slow. So the second part of this question is about the decade counter, and we're trying to create this sequence from the decade counter. So we need to light up these in turn. So when it starts, we want the red to be high, like that, and then that will light up the red one. And we want the other ones to be dark or dim. So then when it moves on to the next pulse on the sequence, we want the yellow one to be high. Get the idea? And then we want the blue one to be high, so that's going to be that one. Then we want the red one to be high again. Then we want the blue one to be high. Then we want the yellow one to be high. Then we want the green one to be high. Oh, green. I'm red-green colorblind, so that's my excuse. And then we want reset to be high. So reset equals 1 at that point there. Right, so to get it to reset, we just connect the 7 back to reset, which they've already done for us. And now what we need to do is we need to create the circuitry to make this work. Well, this is really easy. If you want the red one to be high, all you do is you get an OR gate, like so, and you connect the output of the OR gate to that red signal there, and we choose any ones that we want it to be red, and we put those as the inputs to this OR gate. So we want it to be on 0 and 3. So we take 0 off, and we take, and for yellow we do the same, another OR gate, and then we want it on 1 and 5. So there's 1, and there is 5, and we connect that up to the yellow. The blue one, oh, they put them in a different order, that's sneaky, right? The blue one is here, so we want 2, and blue also we want 4, and then finally the green one, the green one only has 1, so we don't even need an OR gate, so we can just, oh, that's why they changed the order, so we don't have to cross any lines for that one. So how long is the blue signal on for in each sequence? Right, well, we need to go back to this. So if the frequency is this, then the time period is equal to 1 divided by the frequency. Now that is equal to 1 divided by 0.098 ... So I've got that number on my calculator. So 1 divided by that is equal to 10.23 seconds. So the time period is 10 seconds-ish. And the blue one is on for once, twice in a full sequence. So it's actually on for 2 times by 10.23, so on twice, for 10.23 seconds each time, which gives you 20.46 seconds, which is approximately equal to 20 seconds in total. Question 8, this is about the amplifier subsystem. You need to know all of these blocks off by heart. So A is the preamps, they follow microphones. B is the mixer or the summing amplifier. And C is the power amplifier, which always comes just before the loudspeaker. Okay, you just need to learn those. Right, now we're going to make block B. So this is going to be a summing amplifier. So complete the circuit diagram. So we need input resistors on both of these. Now both of these connect to the inverting terminal. We need a feedback resistor, RF, so that's going to be R1, we'll call that R2. That goes to the output, and this connects down to ground, 0 volts like that. You need to know those diagrams off by heart. You can tell it's an amplifier because it's got negative feedback. It's going to invert because we've got the 2 inputs connected to the inverting terminal. What's the purpose of block C? So block C is to increase the current for the loudspeakers. The loudspeaker can develop lots of power, make lots of noise. So to boost the current to the loudspeaker to increase, or to develop a lot of power in the speaker, making noise. Well, I suppose sound might be a better word than noise. Sound. It's all about the power. So you want to, and you get the power by increasing the current. This has already boosted the voltage, and these are boosting the voltage, but then you need P is equal to IV. So there's 2 parts to the power. you've got the voltage side and you've got the current side. So this is the bit that develops the current. And here we are at question 9, the QER question. So remember, for these questions, it's not just about what you write down, but it's also about how you explain yourself and putting your answer in a sensible, logical way, and that will give you access to all of the marks. Even if you said everything right, but your answer was impossible to follow, then you wouldn't get past the 1 or 2 mark stage threshold. So we have a system here for a tropical fish aquarium, and it's got a switch and it's got a thermistor, so some sort of temperature sensor there, and it's got an AND gate here, it's got a MOSFET with a heater. The specification for the design: the heater should operate when either the temperature drops below 25 degrees C or a switch is pressed. Well, that OR is a big clue. That's an AND gate. It needs to be an OR instead, doesn't it? Because it's OR there. When switch 1 is pressed, point A should be at logical 1. Yes, so that's going to be okay. When the water temperature drops below 25 degrees, point B should be at point 1. So let's just scribble in the margin a bit. The resistance of a thermistor against its temperature looks like that. So voltage B against temperature. Well, when this is very, very hot, this is going to have a low resistance, so the voltage B is going to be high up. And when this is very, very cold, then it's going to have a huge resistance, so B is going to be close to 0. So it's going to sort of look like that. So when the water temperature drops below 25 degrees, B should be at logical 1. So that's the opposite way around. Evaluate the function of the design against the specification and suggest any changes to fully meet the specification. Okay, so there's various ways we can organize our ideas. We could work our way through the specification, or we could work our way sort of through the circuit like that. I think I'm going to work my way from left to right through the circuit, just as a change to last time I did this question here. So I'm going to divide this up into subsystems. So we're going to have this as A, B, C, and D, like that, and then I'm going to have my answer in terms of A, B, C, and D. So this is subsystem A. So I'm going to talk about subsystem A. When the switch is pressed, it will pull voltage A up to 9 volts. So when the switch is pressed, it pulls VA up to 9 volts. So that's a logic 1. And does that agree? So that's switch SW1. Sorry, when switch SW1 is pressed, it pulls this up, voltage A up to 9 volts, which is a logical 1. And I'm going to number these as well. This is correct as per specification point 2. Okay, so we've done subsystem A. So now I'm going to do subsystem B. So subsystem B, as the temperature rises, voltage B, oh no, we want to talk about the thermistor first. So what happens as the temperature rises, the resistance of the thermistor reduces. So voltage B rises. Okay, so does that meet the specification? This does not meet spec 0.3 there. It's supposed to, as it rises, become a as the temperature falls, it's supposed to become a logical 1. So this does not meet spec 0.3. So to fix this, well, we could do various things. We could put a NOT gate here, or we could switch the thermistor and the 10K around. 6 to 1, half dozen the other. I'm going to switch the thermistor and the 10K around. To fix this, swap the thermistor and the 10K around. Let's just make sure that it's plain as day. By drawing a little diagram now. Okay, so we've done this one and this one. So now subsystem C. So currently both S1 or SW1 and, let's write it out in full, and VB have to be high for the MOSFET to be triggered. This does not meet specification points, and we're doing specification point 1 here. Replace the AND gate with an OR gate. Okay, so we've suggested our fix there. We need it to be OR because that word there. And then part D. Now this is something that lots of students forget. This bit works perfectly. It's not really mentioned in the specification, but we should mention it, that it works perfectly. D, when, let's label it C, VC is high, the MOSFET will be on and the heater will get hot. So this works as intended. Okay, so make sure you always mention the bits that work as well as the bits that don't work. Right, so it doesn't matter how you organise your answer. What matters is that you do organise your answer. Actually, this one has worked out very neatly, dividing into subsystems. I would very strongly recommend that you write on the diagram and on here and refer to them. Your examiner will see the whole page. When they get this, they will be able to look at your diagram. So if you've written on the diagram and identified bits, it makes referring to things much easier. We've hit the quality of English because what we needed to do was to organise our response, and we've organised it nicely with different subsystems. We have evaluated the function in each case. That was the first line. We evaluated what it did. We then compared that with the specification. That's what we did, and then we suggested any changes. So we've done that. So we did that, we did that, and we did that, and we did it for each subsystem separately. The last question. The heater is rated at 9 volts, 4 amps. The MOSFET has a value of GM 0.1 Siemens. Calculate the minimum voltage, the logic gate, for this to work. So we're going to need our equation for MOSFETs, which is this one. ID is equal to GM VGS minus the threshold voltage, which they always decide is 3 for you. So let's just shove the values in straight away. So we want the current flowing down here to be 4 amps. So we put 4 is equal to, the GM is 0.8, VGS is what we're trying to find, minus 3. It's much easier to just shove the numbers in than it is to rearrange the equation first. So we're going to do 4 divided by 0.8 is 5. So 4 divided by 0.8 is equal to VGS minus 3. So that's 5 is equal to VGS minus 3. So VGS is equal to, well, move the 3 over there, 5 plus 3, 8 volts minimum. And that's the paper. Good luck in your exams, if you're lucky enough to have exams.